Imagine for a moment that you are standing in a room. The room is perfectly square. Every wall is the same distance from you. Every corner is identical. The ceiling and floor are equidistant. You are, by every measure, at the center of something symmetrical. Now imagine that the room begins to expand. Not from one wall outward, but from every wall simultaneously. The ceiling retreating upward at the same rate the floor drops away, the left wall pulling back as fast as the right. Everything growing, everything stretching, but perfectly, evenly, symmetrically. That is what most people picture when they think about the expanding universe. A tidy, orderly balloon being inflated uniformly in all directions by some invisible hand. Calm, consistent, predictable. The cosmologists sorted that in the 1920s, didn't they? Expansion confirmed, Nobel Prizes issued, textbooks written, move along. Except the universe didn't read the textbook, because here is what we have actually discovered, quietly, over the past few decades, as our instruments have grown sharper and our surveys have reached deeper. The universe is not expanding the same way in every direction. The room is not symmetrical. Some walls appear to be racing outward faster than others. The space between galaxies on one side of the observable universe appears to be stretching at a different rate than the space on the opposite side. And if that sounds like it might be a minor technical quibble, a rounding error, a measurement artifact that cleverer instruments will eventually smooth away, it is not. Because physicists and cosmologists have checked their work repeatedly. With different telescopes, different methods, different teams on different continents, all arriving at variations of the same uncomfortable result. The universe appears, in some profound and measurable sense, to be lopsided, and that single word, lopsided, if it turns out to be the correct word, has the power to dismantle one of the most foundational assumptions in all of modern physics. The assumption that, at the largest scales, the universe looks the same in every direction. That the laws governing the cosmos apply equally whether you are pointing your telescope toward the constellation Virgo or toward the opposite point in the sky. The assumption so fundamental that science gave it a name and buried it inside the bedrock of cosmology, rarely questioning it, because to question it would be to pull at a thread that might unravel everything. That assumption is called the cosmological principle, and right now, in the laboratories and observatories and conference rooms where the people who actually count galaxies for a living spend their days, the cosmological principle is having a very bad century. We live in a moment that is strange and extraordinary in the history of cosmology. Strange because the data keeps suggesting something that the dominant theory insists cannot be true. Extraordinary because we have, for the first time, the instruments sensitive enough to actually detect discrepancies at the scales where the universe's deepest properties reveal themselves. For most of human history, the universe was a ceiling of points of light above a flat Earth. Then it was a solar system, then a galaxy, then a cosmos of billions of galaxies. At each expansion of our horizon, we found that the universe was larger, stranger, more intricate, and less intuitive than the picture we had been carrying. Every time we thought we understood the shape of the thing grew a new wing. And now, at the frontier of the deepest surveys ever conducted, the universe appears to be doing it again, showing us a feature we did not plan for, a grain to the fabric, a direction to the expansion, a crack in the symmetry we had assumed was there all along. This is the story of how we built our understanding of the expanding universe, how we came to believe it was uniform and symmetric, and how the data, stubborn, uncooperative, occasionally infuriating data, has begun to suggest something stranger and more disorienting than almost anyone predicted. This is also the story of the scientists who did the work, the ones who made the original discoveries, the ones who challenged them, and the ones who are right now, at this moment, running analyses on datasets so large that the results take weeks to emerge from computing clusters the size of shipping containers. It is a story about the courage required to publish a result that contradicts the established framework, and about the discipline required to remain skeptical even of results you find thrilling. It is, at its heart, a story about the difficulty of knowing the universe from inside it, using instruments made of the same matter the universe made, measuring a sky we were born underneath and have always assumed was simply there, unchanged, unbiased, waiting patiently for us to read it correctly. Let us go back to 1929, back to a small office at the Mount Wilson Observatory in the hills above Pasadena, California, where a tall, quietly ambitious astronomer named Edwin Hubble was sitting with data that would change what it meant to be human. Hubble had been measuring the light from distant nebulae, what we now call galaxies, using a technique developed in part by his colleague Vesto Slipher, who had noticed something peculiar about the spectra of light coming from these objects a decade earlier. Light from a source moving away from you stretches out. The wavelengths get longer. They shift toward the red end of the spectrum, a phenomenon called redshift, analogous in light to the way the pitch of a receding ambulance drops as it moves away from you. Slipher had found, to his considerable surprise, that almost all the nebulae he measured were redshifted. Almost all of them were moving away from us. That alone was strange. But Hubble added something crucial. He found a way to measure how far away these galaxies were, using a class of pulsating stars called Cepheid variables, whose intrinsic brightness is known and predictable. They brighten and dim on a schedule, and the length of that schedule tells you how intrinsically bright the star is, so that by comparing its apparent brightness with its known true brightness, you can calculate its distance. They are, in effect, the universe's own distance markers, standard candles flickering at a measurable rate. When Hubble plotted distance against recession velocity for a sample of galaxies, something extraordinary emerged. The farther away a galaxy was, the faster it was moving away, not randomly, not messily, linearly, a straight line on a graph, a constant ratio between distance and velocity. He published this relationship in 1929, and it became known as Hubble's law. It describes, with deceptive simplicity, the expansion of the entire universe, and it carries within it the implication that set Einstein fidgeting, and clergy praying, and a generation of physicists recalculating their entire picture of the cosmos. If everything is moving away from everything else, then run the film backward and you arrive at a point, a single point, where everything was together, a beginning, an origin. What the Belgian priest and physicist Georges Lemaitre had already been proposing in theoretical papers since 1927, and what the British astronomer Fred Hoyle would later mockingly call the Big Bang in a 1949 BBC radio broadcast, and not realizing that the name would stick with a tenacity that good ideas often achieve and bad nicknames always do. The implication landed unevenly. Einstein had already published his field equations of general relativity in 1915, and those equations had an awkward habit of producing a dynamic universe, expanding or contracting as a natural solution, whether you wanted one or not. Einstein himself found this so philosophically unsatisfying that he added what he called the cosmological constant to his equations, a fudge factor designed to make the universe stand still, a kind of mathematical stabilizer for a cosmos that his own equations refused to hold in place. When Hubble's data arrived and the expansion of the universe became observational fact, Einstein is reported to have abandoned the cosmological constant and called it the greatest blunder of his career. This is a remarkable statement from a man who also invented special relativity, general relativity, and the photoelectric effect in a single year. But the cosmological constant, as we will discover, had a future Einstein could not have imagined. Hubble's discovery also contained at its birth an assumption. A necessary assumption, the kind you need to make to build any model at all, but an assumption nonetheless. The relationship between distance and recession velocity appeared to be the same in every direction he looked. He was not looking very far by modern standards. His sample of galaxies was tiny, his instruments limited to what the 100-inch Hooker telescope at Mount Wilson could resolve. Yeah, and the portion of the universe accessible to him was a minuscule slice of what would eventually be mapped. But the data appeared consistent, and so the model that grew from his work carried within it the idea that the expansion was isotropic, the same in all directions, and homogeneous, the same everywhere in space. These two properties together constitute what cosmologists call the cosmological principle. It was embedded in the foundations of every model that followed. And for 70 years, roughly speaking, nobody had instruments sensitive enough to seriously test it at the scales where deviations might become visible. The assumption was not unreasonable. Looking at the night sky, the distribution of stars appeared broadly uniform in ancient times, before telescopes revealed that they were organized into a galaxy, before larger telescopes revealed that there were other galaxies beyond ours, before surveys revealed that those galaxies were organized into clusters and filaments and voids. At each scale, the universe initially appeared more uniform than it turned out to be. The cosmological principle was the extrapolation of this apparent uniformity to the very largest scales. The philosophical bet that if you zoomed out far enough, the lumps and filaments would average away, and space would look the same in every direction. It was a reasonable bet. But bets, even reasonable ones, sometimes lose. Before we can understand what the data is now suggesting, we need to understand the scale of what we are actually talking about. Because the numbers in cosmology are the kind that the human brain simply cannot process in their raw form. The only way to make them meaningful is to translate them into something with an emotional dimension. The observable universe, the sphere of space we can in principle detect, bounded by how far light has had time to travel in the 13.8 billion years since the Big Bang, is approximately 93 billion light-years across. A light-year is the distance light travels in a single year, and light travels at 299,792 kilometers per second. If you set off from Earth in a car at highway speed, 100 kilometers per hour, and drove without stopping toward the nearest star beyond our Sun, Proxima Centauri, you would arrive in approximately 43 million years. Proxima Centauri is 4.24 light-years away. The observable universe is 93 billion light-years in diameter. Those two numbers are not from the same conversation. Let us try a different approach. Shrink the entire observable universe down to the size of the Earth, a sphere about 12,700 kilometers across. In that model, a single light-year in the real universe corresponds to roughly the width of a strand of human hair. The Milky Way galaxy, which contains somewhere between 200 and 400 billion stars and takes light 100,000 years to cross from one edge to the other, would appear in your model as a disk roughly the diameter of a small coin. Andromeda, the nearest large galaxy to ours, would be another small coin about a meter away. The Virgo cluster, the nearest large cluster of galaxies, would be a dense handful of coins about 50 meters from where you are standing. And the structures we are about to discuss, the great walls and supervoids and filaments of the cosmic web, would be features several kilometers across in your model, spread across a sphere the size of our entire planet. The distances involved are not large in the way that a mountain is large, or an ocean is large, or even the solar system is large. They belong to a different ontological category of largeness entirely, one that human intuition was not designed to navigate without assistance. This matters because the directional variations in expansion rate that the data suggests are not visible at small scales. They appear only at hundreds of millions or billions of light years, the very largest scales our surveys can probe. At those scales, the individual galaxies are invisible. What you are measuring is the statistical behavior of enormous populations of objects, tens of millions of galaxies or millions of quasars, their average positions, their average brightnesses, their average recession velocities. You are doing statistics on the universe at the scale of the universe itself, which is both the most ambitious thing science has ever attempted and the context in which even small systematic errors can masquerade convincingly as cosmological signals. This is why the debate is so intense and why it has lasted so long without resolution, and why the scientists involved are neither reckless catastrophists nor defensive gatekeepers. They are people doing extraordinarily difficult work at the absolute limit of what is currently measurable. Now we need to dig into the physics, because to understand why a directional difference in expansion rate is so alarming, you need to understand what drives the expansion in the first place. And to understand that, you need to understand dark energy. And to understand dark energy, you need to accept that the word understand is carrying a great deal of weight in that sentence, and that some of what follows is honest uncertainty dressed in the clothing of confident explanation. Begin here. In 1998, two independent teams of astronomers were doing something conceptually straightforward, measuring the brightness of a particular type of exploding star called a Type 1a supernova. These supernovae are extraordinarily useful to cosmologists because they explode with a consistency that nothing in nature has any obligation to provide, but which physics, thankfully, enforces. They occur when a white dwarf star, the dense cooling remnant of a star like our Sun, accretes mass from a companion star in a binary system until it crosses a very specific threshold, 1.4 times the mass of our Sun, a limit known as the Chandrasekhar limit. At that point, the white dwarf cannot support itself against gravity, and it detonates in a thermonuclear explosion of extraordinary violence and extraordinary consistency. The peak brightness of the explosion is, with some corrections, reliably similar from event to event, which means that if you measure how bright such a supernova appears in your telescope, and you know how bright it actually is, you can calculate exactly how far away it must be to appear that dim. It is the same logic you would use to estimate how far away a streetlight is from the brightness of its glow. Type 1. A supernovae are bright enough to be seen across billions of light-years of space, making them the most powerful distance indicators in the cosmological toolkit. The High-Z Supernova Search Team, led by Brian Schmidt and including a young postdoc named Adam Rees, and the Supernova Cosmology Project, led by Saul Perlmutter at Lawrence Berkeley National Laboratory, were using these supernovae to measure how the universe's expansion rate had changed over cosmic time. The expectation, backed by solid theoretical reasoning and decades of assumption, was that the expansion should be decelerating. Gravity, acting on all the matter in the universe, pulling every galaxy toward every other galaxy, should be putting the brakes on. The question was simply how much. Would it slow enough to eventually reverse and cause a big crunch, or would it slow gradually and expand forever, becoming ever more cold and diffuse? Nobody was seriously asking whether it might not be slowing at all. What both teams found independently in 1998 was that distant Type 1a supernovae were fainter than they should be, which meant they were farther away than the decelerating expansion model predicted, which meant the universe was not decelerating at all. The expansion was accelerating. The universe was expanding faster and faster as time went on. Something was pushing outward against gravity with increasing effectiveness, something pervasive, something filling all of space with a repulsive energy that had no explanation in the physics anyone could lay hands on. They called it dark energy. Perlmutter, Schmidt, and Rees shared the Nobel Prize in Physics in 2011. The discovery sits in the top tier of the most consequential results in the history of science. And dark energy, by current estimates derived from all available cosmological data combined, makes up approximately 68% of the total energy content of the universe. Ordinary matter, atoms, protons, electrons, stars, planets, every galaxy you have ever heard of, constitutes roughly 5%. Dark matter, which we know exists because of its gravitational effects on galaxies and clusters, but have never directly detected, makes up about 27%. We understand, in any meaningful chemical or physical sense, approximately 5% of the universe. The remaining 95% is mystery wearing two different hats. The standard model of cosmology, called lambda CDM, where lambda refers to the cosmological constant and CDM stands for cold dark matter, incorporates dark energy through the cosmological constant, lambda. It is a constant, meaning by definition it has the same value everywhere in space and at all times. It is isotropic. It acts the same in all directions. It is homogeneous. It does not vary from place to place. These are not measured properties of dark energy. They are assumed properties built into the model for mathematical tractability and theoretical parsimony, and then tested against observations. And for a long time, the observations agreed well enough to avoid alarm. But what if dark energy is not constant? What if it varies across space, having a slightly different strength or character in different regions of the universe? You would expect, in that case, to measure a different expansion rate depending on which direction you pointed your telescope. And here is the connection to everything else in this story. Several independent datasets now suggest something broadly like this, not loudly, not unambiguously, but persistently, like a noise in the walls of a house you cannot quite locate. The most famous single piece of evidence in this debate is not about directional anisotropy at all. It is the Hubble tension, and it arrived quietly, but has since become one of the loudest arguments in contemporary cosmology. The Hubble constant, Hubble's original measure of the expansion rate, the ratio of recession velocity to distance, should be a single fixed number describing the universe right now. In practice, measuring it turns out to depend enormously on how you measure it. There are two fundamentally different approaches, and they disagree with each other at a level that statistics says should not happen by chance. The first approach is to look backward in time using the cosmic microwave background radiation. This is the thermal afterglow of the Big Bang itself, a light emitted when the universe was approximately 380,000 years old. Not the first light, but the first light that could travel freely through space without being immediately absorbed, released when the universe cooled enough for protons and electrons to combine into neutral hydrogen atoms, and the cosmos became, for the first time, transparent. That light has been traveling ever since, and it is now detectable as a faint microwave glow coming from all directions equally, at a temperature of 2.725 degrees above absolute zero. It is not perfectly uniform. There are tiny fluctuations of about 1 part in 100,000, and those fluctuations encode information about the early universe with extraordinary fidelity. The European Space Agency's Planck satellite spent 4 years, from 2009 to 2013, mapping these fluctuations with the highest precision ever achieved. By fitting the pattern of fluctuations to the standard cosmological model, the Planck team derived a value for the Hubble constant of 67.4 kilometers per second per megaparsec, with an uncertainty of less than 1%. A megaparsec is about 3.26 million light-years. So for every 3.26 million light-years of distance between two objects, those objects are moving apart at 67.4 kilometers per second due to cosmic expansion, a precise, well-founded measurement. The second approach is to look at the local universe directly, using the cosmic distance ladder, a chain of overlapping measurement techniques that begins with parallax for nearby stars, progresses through Cepheid variable stars for nearby galaxies, and culminates in Type 1a supernovae for the most distant measurements. Adam Rees, using the Hubble Space Telescope and subsequently the James Webb Space Telescope to calibrate this ladder with increasing precision, consistently finds a value around 73 kilometers per second per megaparsec. That is not 67.4. The gap is about 8%. And with the current measurement precision of both methods, that gap is statistically significant at roughly 5 sigma, the same threshold particle physicists use when claiming to have discovered a new fundamental particle. 5 sigma is not a coincidence. 5 sigma is not a calibration oversight. 5 sigma, in physics, is the standard for discovery. And the Hubble tension is 5 sigma, which means that either one or both measurement chains contains an unidentified systematic error, or the standard cosmological model is incomplete, or the universe is doing something that our model does not account for. All 3 possibilities are deeply interesting, and one of them, the idea that the local universe we happen to inhabit expands slightly faster than the global average, connects directly to the question of directional asymmetry in the expansion rate. If dark energy varies across space, different regions of the universe will have different local expansion rates, and the local region our instruments occupy would be a biased sample of the whole. This is not the only explanation of the Hubble tension, and probably not the simplest one. Theorists have proposed early dark energy, a burst of additional repulsive energy in the first fraction of a second after the Big Bang, as one resolution. Others have proposed modifications to general relativity itself, or interactions between dark matter and dark energy, or the possibility of additional neutrino species affecting the early universe's expansion. These ideas all involve changing the model at various epochs to make the 2 measurements agree. None of them has been confirmed. The tension stands. Now let us move into the universe itself. Let us travel through the data the way you would travel through a landscape, not cataloguing it from a distance, but moving through it, arriving at its features one by one and letting each one reveal something the last one could not. Begin close. By cosmic standards, embarrassingly close. Our galaxy, the Milky Way, is a barred spiral galaxy containing between 200 and 400 billion stars, and arranged in a disk approximately 100,000 light-years across and about 1,000 light-years thick, with a central bar of stars and 4 major spiral arms winding outward. We sit in one of the minor spurs, about 26,000 light-years from the galactic center, which houses a supermassive black hole called Sagittarius A star, with a mass equivalent to roughly 4 million suns. The Milky Way is our home address at the scale where addresses start to mean something cosmologically. We sit within a modest collection of galaxies called the Local Group, roughly 80 galaxies in total, most of them small dwarf galaxies, along with the Milky Way, Andromeda, and a handful of intermediate-sized companions. The Local Group occupies a volume roughly 10 million light-years across. In the context of the observable universe, it is not quite a rounding error, but it is close. Zoom out to 100 million light-years, and you can see that the Local Group sits at the edge of the Virgo supercluster, a gravitationally linked collection of galaxy groups dominated by the Virgo cluster at its center. A dense, turbulent knot of more than 1,300 galaxies, the gravitational center of a region so massive that it exerts a measurable pull on the Milky Way itself, slowing our recession from it relative to the overall expansion of space. For decades, the Virgo supercluster seemed like the neighborhood. It was large enough to be impressive and poorly enough mapped to seem comprehensive. It was neither. In 2014, A team led by R. Brent Tully of the University of Hawaii published a remarkable paper in Nature that redefined what a supercluster was. Using a new technique for mapping the flow of galaxies through space, their peculiar velocities, the movements driven not by cosmic expansion, but by the gravitational pull of concentrations of matter. The team traced the boundaries of the gravitational basin of attraction that the Milky Way sits within. They found that the Virgo supercluster is not itself a supercluster in the meaningful sense. It is just one lobe of an enormously larger structure, a supercluster of superclusters, to which they gave the Hawaiian name Laniakea, immeasurable heaven. Laniakea is 520 million light-years across. It contains approximately 100,000 galaxies. It encompasses a total mass equivalent to 100 quadrillion suns. Our galaxy, our local group, our local supercluster, all of it is contained within one arm of this structure, flowing gravitationally toward its center like water running toward a drain. Except that the drain is a region of space called the Great Attractor, a gravitational anomaly behind the Milky Way's own disk that has been pulling our local neighborhood through space for as long as we have been able to measure it, hidden for most of that time by the dust and stars of our own galaxy obscuring the view in that direction. The discovery of Laniakea was beautiful and humbling. It revealed that the address of the Milky Way, if written completely, would include a structure 500 million light-years across that had been there all along and simply been too large to see. And Laniakea is not unusual. There are comparable structures scattered throughout the observable universe. The universe is tiled with them, separated by the vast networks of filaments and voids that constitute the cosmic web. The cosmic web is the term cosmologists use for the large-scale structure of the universe at scales above roughly 100 million light-years. It is a network of filaments, thread-like structures of galaxies and dark matter stretching across hundreds of millions of light-years, that intersect at nodes where the densest galaxy clusters sit, like dewdrops at the intersections of a spider's web. Between the filaments lie the voids, enormous regions of relative emptiness, hundreds of millions of light-years across, containing very few galaxies, their matter having been gravitationally drawn away over cosmic time toward the surrounding filaments. The voids are not empty in the strict sense. There are still galaxies in them, just far fewer than average, but they are empty enough that standing inside one, your night sky would be dramatically less populated than ours. You might look outward for hundreds of millions of light-years before seeing a significant galaxy cluster in some directions. The cosmic web is not random. It is the predictable result of the density fluctuations that existed in the early universe. Quantum mechanical variations in the density of matter and energy in the first fractions of a second after the Big Bang, amplified by gravity over 13.8 billion years into the filaments, walls, clusters, and voids we see today. Computer simulations of the universe's evolution, starting from measured initial conditions in the early universe, reproduce the cosmic web with remarkable fidelity. The simulations match the observations. This is one of the great triumphs of the standard cosmological model. It predicted the structure of the universe before that structure had been fully mapped. But the specific structures that have been mapped, named, measured, catalogued, have occasionally outrun the simulation's predictions. The Sloan Great Wall, discovered in 2003 from data in the Sloan Digital Sky Survey, stretches approximately 1.37 billion light-years across and was, at its discovery, the largest known structure in the universe. It held that distinction for a decade before being supplanted by the Hercules Corona Borealis Great Wall, identified in 2013 from gamma-ray burst distributions and estimated to be somewhere between 6 and 10 billion light-years across, a structure that large technically strains the cosmological principle. The The principle predicts that at scales above roughly 300 to 400 million light-years, the universe should appear smooth and featureless, with the lumps averaging out. A 10 billion light-year structure does not average out. It is a counterexample to homogeneity at a scale the Standard Model was not supposed to allow. There is also the Bootes void, discovered in 1981 when astronomer Robert Kirshner and colleagues were running a survey and found in a region of sky in the constellation Bootes essentially nothing. No galaxies where galaxies should have been. A spherical underdensity, roughly 330 million light-years across, sitting in a universe that, by the cosmological principle, should not have produced anything quite that empty. When Kirshner described it, he made the observation, only slightly hyperbolic, that if the Milky Way had been located in the centre of the Bootes void, we would not have discovered the existence of other galaxies until the 1960s. The nearest galaxies would have been so far away, in such low numbers, that earlier instruments could not have reached them. We would have looked out into a void and concluded that the Milky Way was the universe. And then there is the cold spot. In the cosmic microwave background, that uniform ancient glow that pervades the sky, the Wilkinson Microwave Anisotropy Probe, operating in the early 2000s, found a region of sky in the southern constellation Eridanus that was measurably colder than its surroundings. Not by much, a few microkelvins below the already tiny average temperature of 2.725 Kelvin. But the cold spot's size and the depth of its temperature deficit were inconsistent with what the Standard Model predicted the microwave background fluctuations should look like. Several explanations were proposed. One was a foreground supervoid, an enormous emptiness aligned along that line of sight, whose gravitational effects would cool photons passing through it. Evidence for such a supervoid was subsequently found by surveys in that region of sky. Another explanation, proposed by some theoretical physicists with understandable excitement and considerable caution, is that the cold spot represents a physical imprint from the collision of our universe with another universe during an era of cosmic inflation, an interaction across the boundary between two bubbles of space-time in a multiverse. That particular explanation is currently unprovable, and most cosmologists regard it as speculative, but the fact that it cannot be ruled out tells you something about where we are. These structures, the Great Walls, the Bootes void, the cold spot, the Great Attractor, are the bioluminescent details of the universe. The small unexpected things that when you hold them up to the light reveal something much larger. And the larger thing they collectively suggest is this: the universe at the very biggest scales is not as uniform as the cosmological principle predicts. It is not wildly different. The models still work broadly, but the universe is lumpier than expected, more structured at extreme scales than the simulations comfortably reproduce. And this underlying structural asymmetry may be the physical substrate on which the directional expansion anomalies rest. Now, the directional measurements themselves. The 2020 paper by Konstantinos Mikas and colleagues at the University of Bonn is the clearest place to start, because its methodology is elegant and its conclusion is stark. Mikas used X-ray galaxy clusters, enormous collections of thousands of galaxies pervaded by superheated gas that glows in X-ray wavelengths, as distance indicators. There is a well-established relationship between the X-ray temperature of such a cluster's gas and its X-ray luminosity. Hotter clusters are intrinsically more luminous. By measuring both temperature and apparent brightness, you can calculate a distance independently of redshift. Then you compare that distance estimate to the distance predicted by the cluster's redshift, assuming a particular Hubble constant. If the Hubble constant is uniform, the two methods agree statistically. If the Hubble constant varies across the sky, they will disagree in a directional pattern. Mikas's team analysed over 800 galaxy clusters and found exactly that. a directional pattern. The Hubble constant inferred from clusters in one hemisphere of the sky was systematically higher than the Hubble constant inferred from clusters in the opposite hemisphere. The difference was approximately 9%, directionally coherent, statistically significant at about 4 sigma, and consistent across subsets of their data. 9% may sound small. In any normal context it would be. But the Hubble constant is one of the most fundamental quantities in cosmology. A 9% directional variation in it would mean the universe is expanding roughly 1/11th faster in one direction than the opposite. That is not a fine-tuning problem. That is a structural feature of the cosmos. That same year, separate analyses of Type I supernovae found hints of directional variation in the inferred Hubble constant at the level of 2 to 3 sigma. Not definitive, but consistent with the galaxy cluster result. And then came the quasar dipole. The 2021 analysis by Seacrest and colleagues used a catalogue of 1.36 million quasars, selected from the CatWise 2020 survey, combining infrared data from the WISE and NEOWISE space telescopes. By counting the number of quasars per unit of sky area in different directions, they were looking for the kinematic dipole, the slight excess of sources in the direction of our motion through the universe and slight deficit in the opposite direction. What they found was a dipole in broadly the right direction, but 2 to 4 times larger in amplitude than it should be if our peculiar velocity were the only cause. That excess amplitude, if real, implies either that the distribution of matter in the universe is not as homogeneous as expected, or that the expansion of space, which determines how densely objects are distributed as a function of distance, varies directionally. Either option is deeply uncomfortable for the standard model. The cosmological fringe has naturally latched onto these results with enthusiasm that occasionally outpaces the evidence. In certain corners of the internet and on conference programs dedicated to alternative cosmologies, the directional expansion anomalies have been recruited as evidence for everything from the electric universe to various tired light theories to the idea that the Big Bang never happened and the cosmological redshift is due to some unknown property of photons traveling through space. These alternatives universally fail to explain the full suite of observational evidence. The acoustic peaks in the microwave background, the primordial nucleosynthesis, abundances of light elements, the large-scale structure of the cosmic web, and they should be resisted on those grounds rather than dismissed for being contrarian. The evidence for the Big Bang is not a house of cards that topples if you pull the cosmological principle out from under it. The evidence for the Big Bang is independent, multiply confirmed, and extraordinarily robust. What is being questioned is not the Big Bang. It is the specific assumption that the universe is perfectly symmetric at all scales. These are very different claims. The evidence is against perfect symmetry, not against the Big Bang. And now we arrive at the pivot, the moment where the shape of the question changes. We have been treating the cosmological principle as the thing potentially being falsified. But step back and consider what it would mean if it is true. If the cosmological principle is perfectly correct and the universe really is isotropic and homogeneous at the largest scales. In that case, every single one of the anomalies described above, the galaxy cluster dipole, the quasar dipole, the hints in supernovae, the structures larger than the model predicts, must be explained by systematic errors in the measurements. Every single one. Not one of them can be real. They must all be noise, calibration errors, selection biases, foreground contamination. And the probability that all of them are noise, individually and collectively, decreases with every additional independent dataset that finds a consistent signal. Here is the analogy. Imagine that you are investigating a famous painting for forgery. You bring in an expert in the type of canvas used, and they say the canvas looks unusual. You bring in a pigment analyst who says one of the pigments used was not commercially available at the supposed date of painting. You bring in a brushwork specialist who says the technique is inconsistent with other authenticated works. You bring in an infrared imaging expert who finds an unusual underdrawing. Any one of these findings alone could be explained away. Unusual canvases are used, pigments have been misdated before, styles vary, underdrawings are not always documented, but all four independently in the same direction. At some point, the most parsimonious explanation is not that four independent experts all made independent errors that all pointed the same way. The most parsimonious explanation is that there is something wrong with the painting. Cosmology is not quite there yet. The signals are strong enough to be taken seriously, not strong enough to constitute proof, but the number of independent investigations pointing broadly in the same direction keeps growing, and the scientific community's response has evolved from mild curiosity to genuine concern to something that feels, at conferences and in preprint servers and in grant applications, like the early stages of a paradigm question. Not a paradigm shift, not yet, and perhaps not for a long time, but a question. One that the instruments of the coming decade are specifically positioned to answer. Let us put what we have done in perspective, because perspective is what keeps this from being merely an exercise in abstraction. When the Sloan Digital Sky Survey began in 2000, it used a 2.5-meter telescope at Apache Point Observatory in New Mexico to photograph the sky in 5 wavelength bands and measure the spectra, and hence the distances of millions of galaxies and quasars. Over 2 decades, it produced 3-dimensional maps of the universe containing more than 500 million astronomical objects and covering about 1/3 of the entire sky. It transformed cosmology. The maps it produced allowed the first precise measurements of the cosmic web, the first detailed statistical analyses of galaxy clustering at large scales, and the first robust confirmations of the acoustic oscillations in the distribution of matter, the imprint of sound waves in the early universe, frozen into the cosmic structure when the universe became transparent. It was one of the most productive scientific instruments in history. The surveys now coming online make the Sloan look modest. The Dark Energy Spectroscopic Instrument, DESI, mounted on the 4-meter Mayall telescope at Kitt Peak National Observatory in Arizona, began its 5-year survey in 2021 and has already, in its first year of science operations, produced maps of 6 million galaxies, maps that will constrain the expansion history of the universe with an accuracy that was simply out of reach before. Its full survey will cover 35 million galaxies and quasars across 14,000 square degrees of sky. It is specifically designed to measure the evolution of dark energy over cosmic time, and it will do so with enough precision to distinguish between a true cosmological constant and a dark energy that varies in strength over time. Early results from DESI's first data release, published in 2024, already showed hints that dark energy might not be constant, that its equation of state may have changed over cosmic history. If confirmed with more data, this would be one of the most important results in decades. The Vera C. Rubin Observatory on Cerro Pachon in Chile, named for the astronomer who spent her career patiently demonstrating, against considerable resistance, that the stars in galaxies were rotating faster than they should be unless there was invisible matter holding them in, will conduct the Legacy Survey of Space and Time beginning in 2025. Over 10 years, it will photograph the entire southern sky every few nights, building the deepest, most comprehensive time domain map of the universe ever constructed. It will detect tens of billions of sources, including supernovae, gravitational lens events, moving objects in the solar system, and transient phenomena across the observable universe. The sheer volume of data will require machine learning systems to sort and classify, operating in real time as each night's observations are processed. It will contain, somewhere within its petabytes, the answer to questions we have not yet thought of. The Euclid Space Telescope, launched by the European Space Agency in July 2023, is orbiting the Sun from the second Lagrange point, the same stable vantage point occupied by the James Webb Space Telescope, and is designed to map the shapes and positions of 1.5 billion galaxies across 10 billion years of cosmic history. By measuring how the shapes of galaxies are subtly distorted by the gravitational lensing of dark matter along the line of sight, and by measuring the statistics of galaxy clustering at different cosmic epochs, Euclid will constrain the properties of dark energy with extraordinary precision. If dark energy varies across the sky, Euclid is the instrument most likely to see it. And then there is what we cannot yet do. We cannot measure cosmic expansion from outside the universe. We cannot compare our local Hubble constant with one measured from a completely different vantage point billions of light years away. We are, by definition, constrained to measure the universe from inside it, from one position in it, using instruments made of the same matter the universe produced. The parallax of our perspective is irreducible. We cannot step outside. We cannot see the other side of the horizon. We cannot reach any of the objects we study. We are in the position of a single observer standing in the middle of a vast, dark plane, trying to deduce its geometry from the pattern of stars above them, without being able to move more than a kilometre in any direction. Our instruments extend our reach enormously. They do not give us omniscience. The universe is under no obligation to be knowable from one location within it. That is the deepest humility this subject demands. Not the humility of admitting we might be wrong about a specific measurement, though that is real and necessary. The humility of recognizing that we might be systematically wrong, that our picture of the universe could be distorted by the very position we occupy within it, in ways we have not yet identified and may not be able to fully correct for. The cosmological principle was the assumption that allowed us to pretend this was not a problem, that our local measurement could stand in for a universal one, that the universe's behavior here is representative of its behavior everywhere. If that assumption is wrong, if the universe genuinely expands differently in different directions, if dark energy genuinely varies across space, if the cosmos has a grain or an axis or a preferred orientation, then we are not just missing a number. We are missing something structural, a feature of the universe itself that our entire framework was built around not having to account for. There is a kind of vertigo in this realization that is worth sitting with for a moment, rather than rushing past it toward resolution. We have spent a century building the most precise, most mathematically sophisticated, most observationally confirmed model of the universe ever produced. We have measured the age of the cosmos to within a few tens of millions of years. We have mapped its large-scale structure across billions of light years. We have detected the gravitational waves from colliding black holes, confirmed the existence of the Higgs boson, photographed the shadow of a black hole, and landed rovers on the surface of Mars. And we still do not know what 95% of the universe is made of. We cannot reconcile our two best measurements of how fast it is expanding, and we are not entirely sure it is the same in all directions. That is a beautiful and uncomfortable place to be. It is exactly the place where science does its best work. The young cosmologists who will spend the coming decades resolving or deepening the Hubble tension and the anisotropy question are right now learning their craft. They are running simulations on supercomputing clusters, writing analysis pipelines for DESI and Euclid and Rubin, attending conferences where the debates are sharp and the stakes feel enormous because they are. They are inheriting a cosmology that has never been more precise and has never been more puzzled. The precision is what revealed the puzzle. The better the instruments, the louder the anomalies became. And the anomalies have not gone away. When Vera Rubin in the 1970s insisted that the rotation curves of galaxies were telling her something real, that the outer stars in spiral galaxies were orbiting too fast to be explained by the visible matter alone, she encountered skepticism from a field that was comfortable with its existing picture. She kept measuring. She measured more galaxies. She measured them more carefully. The anomaly remained. And eventually the field had to accept that there was something there. Dark matter, and invisible and fundamental, constituting most of the mass of every galaxy in the observable universe. The rotation curves were not wrong. The picture was incomplete. Something similar may be happening now with the directional expansion of the universe. The measurement teams are not amateurs. The signals are persistent. The independent confirmations are accumulating. Perhaps they will dissolve when better data arrives. The history of science includes many such dissolutions, and scientific honesty demands that this possibility remains central. But if they do not dissolve, if the surveys of the next decade confirm that the universe expands measurably faster in one direction than another, we will be in the most extraordinary epistemic position in the history of cosmology. Not having failed to understand the universe, having succeeded, even for the first time, in understanding it well enough to detect its asymmetry, having built instruments sensitive enough to hear the universe's grain, having asked with sufficient precision whether our room was actually square, and having discovered, after all this time, after all these centuries of looking up and making maps and building equations, that the room was tilted, that some walls were always moving faster than others, that the universe, in its immensity, has a direction. We did not know that when Edwin Hubble drew his line on a graph in 1929. We are only beginning now, in the third decade of the 21st century, with telescopes in space and computing clusters the size of buildings and international collaborations spanning 40 countries, to hear what the universe has been trying to tell us all along. The question is not whether we will eventually understand it. The question is whether we are ready for what understanding it might cost. The specific direction in which several of these anomalies point deserves more attention than it usually receives in general discussions of the topic, because it is one of the features that makes the signal both more compelling and more suspicious at the same time. Most of the directional anomalies, the quasar dipole, the X-ray cluster, anisotropy, certain features in the supernova analyses, converge on a direction in the sky that is broadly consistent with the direction of what is called the CMB dipole, the slight asymmetry in the cosmic microwave background caused by our motion through the universe. The CMB dipole points toward the constellation Leo, roughly, and represents our solar system's motion at about 370 kilometers per second relative to the cosmic rest frame, a velocity that is itself the result of our galaxy's motion within the local group, the local group's infall toward Virgo, and ultimately the pull of the great attractor, all summed together into a single vector of peculiar motion. The fact that the anomalies tend to align with the CMB dipole direction is, depending on your perspective, either the most suspicious or the most interesting thing about them. Suspicious because it raises the obvious possibility that the anomalies are artifacts of an imperfect correction for our peculiar velocity. When researchers measure the distribution of objects across the sky, they must subtract our own motion through space. Otherwise, the Doppler boost we receive in the direction we are moving would masquerade as a real excess of sources. If this subtraction is done incorrectly, if the assumed peculiar velocity is wrong in its magnitude or its direction, a false anisotropy of exactly this type would result. Interesting because, if the correction has been done correctly and a residual signal remains in that same direction, it suggests something even more fundamental, that the universe's actual expansion rate has a gradient aligned with, or at least near, the direction our local supercluster is falling toward. That would be a strange but not entirely inexplicable coincidence if the large-scale structure of the universe in our vicinity creates a genuine directional bias in the local expansion. This is where Sabine Hossenfelder and others have pushed a distinct but related point. Hossenfelder, a theoretical physicist whose work on the sociology and philosophy of physics has made her a prominent and sometimes controversial voice in the field, has argued that the persistence of anomalies in cosmology, the Hubble tension, the sigma-8 tension, the anomalous large-scale structures, the directional signals, collectively suggest that the standard model of cosmology is not being held to the same falsifiability standards applied in other areas of physics. When a model has multiple tensions, multiple anomalies, multiple free parameters that can be adjusted to absorb discrepancies, the scientific community sometimes has a tendency to adjust rather than abandon. This is not scientific dishonesty. It is the completely rational behavior of scientists who have a model that works very well in most respects and are reluctant to throw it away over signals that might still dissolve. But it is worth noting that the lambda CDM model now has 6 free parameters that must be measured from observation, and that every time a new tension appears, the proposed solutions tend to add more parameters rather than reduce the model's complexity. A model that can always be extended to absorb anomalies is a model that becomes progressively harder to falsify. The sigma-8 tension, mentioned above, is worth briefly explaining because it adds another thread to the fabric of anomaly. Sigma-8 is a measure of the clumpiness of matter in the universe, essentially how strongly matter has clustered together under gravity. Measurements from the cosmic microwave background, which tell us what sigma-8 should be if the standard model is correct, predict more clumping than weak gravitational lensing surveys in the local universe actually observe. The matter in the local universe appears to be somewhat less clumped than the early universe data suggests it should be. This tension is not as sharp or as famous as the Hubble tension, but it points in a consistent direction. The local universe may not be precisely representative of the global average that the microwave background is measuring, which would mean that the measurements we make from here are systematically slightly biased by where we happen to be, which is exactly what a universe with a genuine directional expansion gradient would produce. The question of what dark energy actually is, not what it does, but what it physically consists of, bears directly on whether directional variation in expansion rate is theoretically possible. In the simplest version of the story, dark energy is the energy of empty space itself, a vacuum energy arising from quantum mechanical fluctuations in the quantum fields that permeate all of space. This is actually predicted by quantum field theory, which consistently produces a non-zero energy density for the vacuum. The problem, and it is the most embarrassing quantitative mismatch in the history of physics, is that quantum field theory predicts a vacuum energy approximately 10 to the power of 120 times larger than what cosmological observations require. That is not a small discrepancy. That is 10 followed by 120 zeros times too large. Physicists call this the cosmological constant problem, and it has been sitting there unresolved since the 1980s. If the vacuum energy were as large as quantum field theory naively predicts, the universe would have expanded so fast in the first instance of its existence that no structure could ever have formed. No galaxies, no stars, no planets, no readers of this narration. The fact that we exist requires the actual dark energy density to be some 120 orders of magnitude smaller than quantum calculations suggest it should be. Either the quantum calculations are wrong in some systematic and as yet unexplained way, or there is a cancellation mechanism that reduces the vacuum energy to nearly but not quite zero, or, and this is where things get philosophically complicated, We are in a universe where the cosmological constant happens to have the value that permits observers to exist. In a multiverse of possible universes with different values, most of which are uninhabitable. The cosmological constant problem is one of the deepest unsolved problems in fundamental physics, and it is directly connected to whether dark energy is truly constant or whether it might vary across space and time. Alternative descriptions of dark energy, called quintessence, treat dark energy not as a fixed property of space-time, but as a dynamic field, a quantum field that can take different values in different regions of space and can evolve over time. If dark energy is a quintessence field rather than a cosmological constant, it is in principle permitted to have spatial gradients, regions where its value is higher or lower than average. Those gradients would produce exactly the kind of directional variation in expansion rate that the surveys are seeing. The DESI data from 2024 provided the first weak but tantalizing observational hint that the dark energy equation of state, the ratio of its pressure to its energy density, which equals -1 for a true cosmological constant, might not be constant, might be evolving over cosmic time. If that hint is confirmed by subsequent data, the cosmological constant is in trouble, and quintessence, with all its capacity for spatial variation, becomes a much more attractive framework. And a quintessence universe is a universe where directional expansion anisotropy is expected, not anomalous. We have now been on a long journey, from the perfectly square room at the beginning to the tilted universe we may actually inhabit. From Edwin Hubble's line on a graph in 1929 to Konstantinos Mikas's X-ray cluster maps in 2020 to Nathan Sechrest's million quasar dipole in 2021 to DESI's dark energy hints in 2024. From the cosmological principle as an unquestioned bedrock to the cosmological principle as a proposition under active investigation. It is worth pausing here before the close to acknowledge the strangeness of the scientific moment we are in. Astronomy and cosmology have a history of delivering shocks. The discovery that the Sun is not the center of the solar system. The discovery that the Milky Way is not the center of the universe. The discovery that the universe had a beginning. The discovery that the expansion of the universe is accelerating. And each of these was not just a factual revision, but a conceptual one. It changed not just what we knew about the cosmos, but what kind of cosmos we understood ourselves to inhabit. The question of whether the universe is isotropic, whether it expands the same way in every direction, is the next item on this list of potential conceptual revisions. And unlike some revisions, which were welcomed because they resolved tensions and simplified the picture, this one would complicate everything. It would not make the physics neater. It would make it stranger, harder, more interesting, and in all likelihood more accurate. The humans who will navigate that complication are inheriting the work of everyone who came before them. Edwin Hubble measuring light in the hills above Pasadena, et Georges Lemaitre imagining the primeval atom in a Brussels laboratory, Vera Rubin spending her career arguing that what the data showed was real, Saul Perlmutter and Brian Schmidt and Adam Rees looking at distant supernovae and discovering that the universe was accelerating when it should have been braking. Konstantinos Mikas mapping galaxy clusters across the sky and finding a gradient where the theory insisted there should be none. These are not names in a textbook. They are people who looked at the universe more carefully than anyone had before, who followed the data even when the data was inconvenient, and who changed the picture of where and what we are. The picture is not finished. It may never be finished in any complete sense. The universe is not obliged to be fully comprehensible from within, but the edge of the picture, the frontier where the questions are alive and the answers are not yet in, is where the most interesting humans in science spend their working lives. That frontier right now runs through the question of whether the universe has a direction. whether space itself has a grain, whether the expansion that began 13.8 billion years ago has been playing fair in all directions, or whether some walls have always been moving faster than others, and we are only now, at last, beginning to hear the difference. The universe does not owe us symmetry. It does not owe us elegance. It does not owe us a cosmos that conforms to the principles we found convenient enough to assume. What it owes us, or rather, what it offers us, is the truth of what it actually is, one careful measurement at a time, in all directions, at every scale we can reach. The work of reaching farther has never been more ambitious. The tools have never been sharper, and the question has never been more worth asking. And yet the work is done by ordinary people in ordinary circumstances, not by oracles or visionaries standing apart from the rest of humanity, but by scientists who drink too much coffee during late-night data runs, who argue about calibration methods at conferences, who worry about their grant applications, who sometimes get it wrong and have to retract papers, and who sometimes get it spectacularly right and have to spend the rest of their careers explaining what they found to a world that finds it difficult to believe. The history of cosmology is full of these people. Milton Humason, Hubble's observing partner, who left school at 14 and drove mules to the top of Mount Wilson before becoming one of the finest observational astronomers of the 20th century, spending years at the telescope measuring the spectra of hundreds of galaxies to confirm the redshift relationship that Hubble had proposed. Vera Rubin, who applied to Princeton's graduate program in the late 1940s and was not even sent an application form because the astronomy program did not accept women, who went to Cornell instead and spent 4 decades producing work that transformed our understanding of the invisible universe. Cecilia Payne-Gaposchkin, who in 1925 correctly determined from spectral analysis that the Sun is composed primarily of hydrogen, was told by her supervisor to soften the conclusion in her thesis because it contradicted the established belief that stellar compositions matched Earth's, and watched as a male colleague reached the same conclusion independently 4 years later and received the credit for it. The history of cosmology is also a history of what it costs to be right before everyone else is ready to believe you. The scientists working on cosmic anisotropy today are not in that position yet. The field has not decided whether to believe them. The anomalies have not crossed the thresholds that would force a conclusion. But they are doing the same thing that all those earlier scientists did, following the data wherever it leads, publishing what they find, building better methods, running better surveys, and waiting for the universe to make up its mind about what it wants to tell us. That patience, that commitment to observation over theory when the two conflict, is not just the method of science, it is its highest virtue. To change your picture of the world because the world has shown you something new, to let evidence displace assumption, is the most radical intellectual act that human beings perform, and it is what cosmology demands repeatedly of everyone who works within it. The universe may be expanding the same way in every direction. The anomalies may dissolve. The cosmological principle may emerge from the scrutiny of the next decade's surveys intact, its foundations confirmed rather than cracked, the signals revealed as the systematic errors that its defenders have consistently argued they must be. That outcome would itself be a significant scientific result, the most precise tests ever conducted of the universe's large-scale symmetry, returning a verdict of guilty as charged, symmetric, isotropic, homogeneous to the limits of our measuring ability. There would be value in that. There would even be, in a way, beauty in it. But if the anomalies are real, if the universe has a direction, if the expansion rate genuinely varies across the sky, and the coming surveys confirm it at 10 sigma or 15 sigma with multiple independent probes all pointing the same way, then we will be in territory that no cosmological theory currently describes, looking at a feature of the universe so large and so fundamental that comprehending it will take a generation of new thinking, new mathematics, and new assumptions about what kind of universe we actually inhabit. Not a smaller universe, not a scarier one, a richer one, a more complicated one that contains, built into its structure at the very largest scale, something we did not know was there, something that has been there since the beginning, expanding unevenly through the dark, waiting with the patience of deep time for the creatures on one small planet, around one ordinary star, in one corner of one galaxy, to build the instruments capable of noticing it. That is the possibility that makes this question worth every hour that every scientist working on it has ever spent. That is why the room you imagined at the beginning matters. Because if some walls were always moving faster than others, then everything we thought we knew about the room is a first approximation. And the real room, the actual physical, measurable room of the universe, is still waiting to be understood.